Okay, so in this video, we're going to go over the mechanism for forming hemiacetals by doing base catalyzed reaction with carbonyls and alcohols. As an example here, we have acetone. We're going to do base catalyzed. So with the arrow here, I'm going to change the catalyst from the acid to base. So put, if we do methanol, for instance, would this be methoxide and methanol? If your alcohol is ethanol, then you do ethoxide and ethanol. If your alcohol is propanol, then you do propoxide and propanol. Okay, so the conjugate base has to match the acid that you're using for your solvent, your polar product solvent. So we're using methanol here, and so that means that we're getting for product the hemiacetal is going to have this R group will be a methyl right here, and then we'll go for base catalysis. Actually, and here's what it says right here. So it says when you do base catalyzed reactions of carbonyls with alcohols or thiols, it produces hemiacetals and hemiketals, and then it stops there. It does not go any further. So for the base catalyzed reaction that we're doing base catalyzed, we're going to stop the reaction here, and we're not going to go any further. We do not make any of this. In the next mechanism we'll do, where we're going to do under acid catalysis, we will see that we can actually go further. But for this one, we're going to stop the reaction right here. So get rid of this here. Okay, so that's the hemiacetal. Now we also call it a hemiketal. And let's do a little bit of a quick nomenclature here to review this. So what is it? An acetal, a ketal, hemiacetal, hemiketal. So if we go back and look at our hydrates, right? So here's a hydrate. So the hydrate is the geminal diol, or the 1,1 diol. This is obviously going to be the 1,1 diol derivative of an aldehyde because you got the aldehydic proton there. This is the 1,1 diol of a ketone. Now, a long time ago, it used to be, the case that if you were doing these on aldehydes, then the aldehydes would form hemiacetals and then acetals. If you're doing these on ketones, then the ketones would form hemiketals and then ketals. But these days, people use those words kind of interchangeably in orgo. So just remember that hemi means halfway through the mechanism. So when I get halfway through the mechanism here, I'm going to say if I have a carbonyl of an aldehyde, that's what I started out with here, or the carbonyl of a ketone, and then I go halfway through the mechanism where I only replace, and I have one of the OHs, here, and then one of them is going to be an ether. But when I go all the way to having both be ethers, then we call it the full-on ketal or the full-on acetal. And we're not going to distinguish between whether or not the aldehyde makes, acetals and the ketal, the hemiketal makes ketals. We'll just call them interchangeably the hemi ones and the full ones. The hemi ones are halfway through the mechanism, so you're still going to have one OH left. The full ones, whether you call them ketals or acetals, are going to have both of the carbonyl bonds replaced with ether bonds. So you have you start out for each one of these, right? You're starting out with so for the top one, we started out with this aldehyde, so it was acetaldehyde. And then for the bottom one, this was acetone. And so as we go through this, we see the acetaldehyde could be the acetaldehyde hydrate, or it could be the acetaldehyde hemiacetal, or it could be the acetaldehyde acetal. Or we could take the ketone and say that we can do the ketone could be the ketone hydrate, or it can be the ketone hemiketal, or it can be the ketone full ketal if we go all the way to completion there. Okay, and one important thing to notice about all of these is that the oxidation state of the carbons is going to be the same in each and every one of these, because I've got an oxygen bonded to I got a carbon bonded to an oxygen 1, 2 twice. Here I've got a carbon 1, 2 bonded to 2 oxygens. Same thing here, carbon, 2 oxygens, carbon, 2 oxygens. So the oxidation state is going to be the same. We're not doing oxidation reduction chemistry here. We're just changing the functional group. Same thing here with the ketone. The ketone's got 1, 2 oxygens. This hydrate has 2 oxygens. This hemiacetal has 2 oxygens, and the acetal or the ketal has 2 oxygens. Okay, so the oxidation state stays the same for each one of these. Okay, so to do the mechanism for this, and what I would really, really strongly encourage you to do before you do the mechanism for the hemiacetal chemistry or the ketal chemistry, is I'd encourage you to go back and look at the mechanisms we did for the base catalyzed formation of the hydrate from an aldehyde, or the acid catalyzed. So if you back and look at both of those mechanisms, the base and acid catalyzed mechanism for this reaction here, you'll find that when we do this with the alcohols instead of the water as our solvent, that's the only thing we're changing, but they're both polar product solvents, and what you'll realize is the mechanisms are exactly the same and have the exact same number of steps. So if you review the mechanism for this one, then these next mechanisms will go really, really easily for you. So let's do the base catalyzed conversion of a carbonyl to the, and we're going to stop this at the hemi stage. It won't go all the way. And we'll get back to that in a second. We'll say, well, wait a minute, why is that? But remember, it's going to stop the reaction at the halfway stage here, and we will not form anything beyond here. Now we do the acid catalyze, we will be able to go all the way to the end of this, where you get to the full-on ketal or acetal. So why is it that when you do the base catalyze, so we're going to do, so I'll put the actual reagent here. I'm going to say our reagents are going to be methanol as a solvent, and so therefore we use methoxide as our base. Okay, so how does the mechanism work? Well, so we're going to take our starting material here. We'll take the acetone. We'll take our methoxide base, which is also a nucleophile. We'll have the nucleophile add the electrophile. Don't break the octet rule. So nucleophile is an electrophile, and then we'll get this as an intermediate. And this alkoxide is going to pull a proton off of solvent, which is methanol. So our general acid here is methanol. So you pull a proton off this, give the oxygen 1 pair electrons back, and that will complete this by making the there you go. And maybe actually move these bonds down a little bit, make it a little more. So that is the hemiacetal of acetone. Okay. Now I can do the exact same mechanism if I want to start off with acetaldehyde, the aldehyde with the proton here. That proton would remain here, and that'd be called the hemiacetal of acetaldehyde, base catalysis. Now, why does the reaction stop here? Because if you think about it, if I'm going to go all the way to the full-on ketal, then I have to do a couple steps in the mechanism where I'm going to remove this OH here, and the way we've always dropped off water in mechanisms is we protonate it, and then we have it plop off as a neutral H2O molecule. And that's what you would do here, is if you can figure out a way to get rid of this OH here, then you can have it act as a leaving group, and then you have another second equivalent of methanol add in, and then you'd have the dimethyl ketal, we call it, the dimethyl ketal of acetone. But remember, if you're going to protonate that oxygen and have it fall off as water, that's going to be a mechanism where you have a plus in the circle at the far inside here. And because I'm doing this a base catalyzed reaction, there's a minus in the circle here. Therefore, if the OH is a crappy leaving group, and it has been all year long, and it's really hard to get it to leave, and it has been all year long, and the only way to get it to leave here is to protonate it and make a plus charge, you can't do it because you can't have plus charges in this mechanism. Okay, so when you do this reaction with base catalysis, it's a good way to take the reaction and get it to go and stop the reaction at the halfway or hemi stage for the hemiketals. The other reaction we'll do then is going to be the acid catalyzed reaction, and we'll look at what the differences are for that. But for this one here, this is the base catalyzed conversion of the carbonyl aldehyde or ketone to the hemi halfway stage for the hemiacetal or hemiketal. And so that is that for this one.